Imagine standing in the middle of an ocean so vast that land exists only beyond the horizon in every direction. Now replace that ocean with space. And replace the water with almost nothing. This isn't science fiction. According to a growing body of astronomical evidence, this might be our real cosmic address. Astronomers are beginning to suspect that the Milky Way, our home galaxy, sits inside a gigantic cosmic void. A region of space so underdense, so empty, that it stretches billions of light-years across. If that's true, it doesn't just change where we are in the universe. It changes how we measure the universe itself. For decades, cosmology relied on a powerful assumption: on the largest scales, the universe is uniform. This idea, often called the cosmological principle, suggests that no place in the universe is special. Wherever you stand, the universe should look statistically the same. But recent galaxy surveys began telling a different story. When astronomers mapped the large-scale structure around our galaxy, they noticed something deeply unsettling. Nearby space contained far fewer galaxies than expected. Not slightly fewer. Dramatically fewer. Galaxy clusters thinned out. Massive structures appeared pushed farther away. And galaxy motions hinted at something even stranger: matter seemed to be flowing outward from our region of space. As if we were sitting near the center of a colossal, ancient emptiness. This region is often referred to as the local void, and estimates suggest it could span up to 2 billion light-years. At that scale, it's no longer a minor feature. It's a structure large enough to challenge the foundations of modern cosmology. At first, many scientists were skeptical. After all, the cosmic microwave background, the afterglow of the Big Bang, appears remarkably smooth and uniform. If a void this massive existed, shouldn't it leave a visible imprint? Not necessarily. The cosmic microwave background shows the universe as it was nearly 14 billion years ago. Voids, on the other hand, take billions of years to grow. What looks uniform in the early universe can evolve into a cosmos filled with filaments, clusters, and enormous regions of near-nothingness. As observational data improved, the evidence for a large underdense region around us refused to disappear. And then another mystery entered the picture. For years, astronomers have struggled with a problem known as the Hubble tension, a disagreement over how fast the universe is expanding. When scientists measure expansion using nearby galaxies, they get one value. When they calculate it using the early universe and the cosmic microwave background, they get a slower one. The difference is small, but persistent. And no one has been able to fully explain it. Some researchers now suspect our location inside a giant void could be part of the answer. Inside an underdense region, gravity pulls matter outward toward denser surroundings. This creates large-scale outflows of galaxies. To an observer inside the void, these galaxies appear to be moving away faster than expected, mimicking a higher expansion rate. In other words, we might be measuring the universe's expansion from inside a gravitational bubble. This doesn't require exotic new physics. It requires something far more uncomfortable: that our cosmic neighborhood is not average. And that assumption of being typical lies at the heart of modern cosmology. If our measurements are biased by our position, then some of our most trusted numbers may need re-examination. The implications go even further. Some scientists argue that in environments as empty as cosmic voids, gravity itself may behave differently. At extremely weak gravitational strengths, traditional Newtonian gravity may no longer fully apply. In these conditions, galaxy motions usually attributed to dark matter could arise naturally, without unseen particles. If that idea holds any truth, voids become more than empty regions of space. They become laboratories for testing gravity at its limits. The standard cosmological model has been extraordinarily successful, but it isn't perfect. Some galaxy clusters appear too massive, too fast-forming, or too extreme to fit neatly into existing simulations. Vast voids only sharpen these discrepancies. If the early universe experienced a rapid inflation meant to smooth out irregularities, why do structures this large exist at all? One possible answer lies in quantum fluctuations in the early universe. Tiny variations, stretched by cosmic expansion, could have seeded enormous structures, including regions where matter never fully condensed into galaxies. Ironically, emptiness may be one of our most powerful scientific tools. Cosmic voids allow astronomers to study the universe without the noise of dense structures. Light passing through a void bends differently, offering clues about dark energy. Galaxy motions inside voids test gravity in its weakest regime. Large-scale flows reveal how structure grows over billions of years. In many ways, voids simplify the universe by stripping it down to its most fundamental behaviors. The final question is unsettling. Are voids like ours rare, making our location extraordinary? Or are they common, meaning the universe is more like a cosmic foam, dense filaments surrounding immense bubbles of near-nothingness? Either answer forces us to rethink what it means to observe the universe from one place. Beyond physics, there is a quieter implication. A universe dominated by vast voids is a universe where isolation is fundamental. Galaxies become islands. Civilizations, if they exist elsewhere, may be separated not just by distance, but by deep cosmic emptiness. Communication and contact become unlikely not because life is rare, but because space itself keeps everything apart. So do we live in a cosmic void? The answer, for now, is cautious. The evidence is growing. The models are improving. And the questions are becoming sharper. Whether this void fully explains the mysteries of cosmic expansion, or merely complicates them, remains open. But one thing is already clear. Our place in the universe may be far less ordinary than we once believed. And sometimes, the biggest discoveries aren't about what we see, but about what's missing.